Let us take stock. Beginning with the definition of conditional probability, we can now fold in as a very simple application of additivity, a principle which allows us to partition a problem into two pieces. And so in an abstract setting, we can find the probability of any desired event by chaining together two conditional probabilities. Now, at this abstraction, it's just an equation, a simple one albeit, but as we've already seen, the applications can be subtle. The devil, of course, is in the details. It resides in how one finds the right partition for a problem. What was at the heart of this simple observation? A key principle. The division of the sample space of possibilities into two disjoint pieces, a partition of the sample space into two components, A and the complement of A. This understanding already shows the way to an abstract generalization, which is useful in its own right. So again, we've begun by partitioning a sample space into two pieces and then figuring out how that partitions an event of interest. If now one moves beyond a partition into two elements and thinks about a partition into, say, a finite number n of events, A1, A2, A3, and so forth, what we now obtain is a finite partition of the sample space into n sets. Recall that a partition means that the constituent sets A1, A2, and so forth are pairwise disjoint. They are mutually exclusive. And together they comprise the entire space. Formally, mathematically, we'll say AI intersection AJ is empty for any pair of indices I and J, and the union of the AIs must be the entire sample space. And the moment we come up with such a partition, we see that a fortiori we have a partition of the event of interest itself, and we can decompose an event of interest H, the target event, into a group of disjoint pieces. That portion of H, which is in A1, stitched together with that portion of H in A2, and so forth. Formally, of course, we are taking the union of a bunch of intersections. The key point here, of course, is because the original sets A1 through AN are disjoint, so are the pieces H intersection A1, H intersection A2, and so forth. Additivity rides to the rescue promptly, and we can now decompose the probability of H as a sum of individual probabilities. Additivity is the whole is equal to the sum of the parts. The moment we have such a decomposition, we see that on the right we have a system of intersection probabilities, and we can promptly chain them together using our definition of conditional probability to come up with a generalization of the basic principle of additivity. It's abstract, but we will see examples and applications in a moment. Before you do that, one more quick extension. The picture suggests a partition of an underlying sample space into a finite number of sets, say n in number. But the argument is clear that it will hold untrammeled even if the partition contains a countably infinite number of sets. And if that's the case, then on the right we'll have an infinite sum chained together of conditional probabilities. This generic principle of additivity in this particular context is, following Kolmogorov's seminal work of 1933, called, rather grandiosely, the theorem of total probability. Informally put, we start with a partition of a sample space into a collection of sets, a collection of events, A1, A2, A3. These events have to be pairwise disjoint, and the union has to be the entire space. We now look at a target event, H. We decompose H into its pieces in each of the AJs, stitch everything together, And the result is a principle of additivity in the context of conditional probability, the theorem of total probability. The summation sign there just says that add over all indices j as aj ranges over all the events in the partition. This collection could be finite, could be countably infinite. Typically, we'll start the index j at 1, 2, 3 and proceed from there. Occasionally, it'll be convenient to start the count at 0, and still more occasionally, it'll be convenient to let j run through all the integers.